Ruhr Valley, 1943. In the darkness stretching across Germany's industrial heartland, a formation of modified heavy bombers advances with a level of precision rarely seen in wartime aviation. The mission is Operation Chastise, an assault built on mathematics, material strength, and aerodynamic control. Below them lie the reservoirs that power the Ruhr's industrial network. Above them, the crews maintain strict altitudes and exact speeds, trusting machines refined to hold stability at moments when even minor structural weakness could alter the entire outcome. Every decision embedded in these aircraft reflects a specific engineering vision shaped years earlier, inside workshops far from the battlefield. As these bombers approach their targets, the success of the operation rests on whether those engineering choices can withstand an environment defined by turbulence, load variation, and the inherent unpredictability of night flying. For viewers following this journey, understanding how such precision became possible adds depth to the entire story that unfolds. The path to this moment begins not above the Ruhr, but inside the British aircraft industry, where a shift in strategic thinking forces designers to rethink how long-range aviation should function. By the mid-1930s, the Royal Air Force faces expanding operational demands. Aircraft conceived for limited payloads and moderate range can no longer support a doctrine increasingly shaped by industrial targets located far beyond Britain's borders. Factories study airflow with greater scientific rigour, wind tunnel research grows more influential, and structural engineers confront the limits of traditional construction. Riveted frameworks that once defined British aircraft design now reveal weaknesses under heavier loads, while aerodynamic efficiency becomes central to every discussion about future bombers. The evolution of air power transforms design offices into laboratories where every modification must be justified by measurable improvements in performance, reliability, and mission endurance. It is within this climate that Roy Chadwick develops a methodology distinguished by its discipline and clarity. Working inside the expanding facilities of Avro, he focuses on the relationship between structural strength, aerodynamic behaviour, and long-term operational demands. Instead of prioritizing isolated performance gains, he approaches each design as an interconnected system shaped by load paths, vibration tolerance, fuel distribution, and manufacturing efficiency. His early work demonstrates a consistent effort to identify failure points before they appear in flight. This mindset leads him to refine fuselage geometry, reinforce key structural nodes, and optimize internal layouts to support larger payloads without compromising stability. The combination of analytical thinking and practical understanding of metal airframes allows him to interpret Air Ministry requirements with uncommon precision, providing solutions that balance innovation with the realities of large-scale production. These principles become crucial as the RAF pushes for aircraft, capable of carrying more equipment across longer distances. Chadwick confronts challenges that require an exact understanding of aerodynamics, materials science, and structural mechanics. Increasing wingspan demands improved torsional rigidity. Higher payloads require rethinking weight distribution across the fuselage. Greater fuel capacity imposes additional stresses on internal members already operating near their limits. Integrating more powerful engines creates new vibration patterns that must be managed through careful alignment and reinforced mountings. Each obstacle is technical rather than theoretical, and solving it requires evaluating how small adjustments influence the overall system. Chadwick's method avoids dramatic leaps and instead builds performance through incremental refinement, ensuring that every modification contributes to an aircraft that behaves predictably in the demanding environment of long-range missions. By the late 1930s, these insights converge into a design philosophy that will soon shape one of the most influential aircraft of the war. Without yet naming the project, the foundations are clear: a strong but lightweight airframe, a spacious internal structure capable of accepting varied payloads, an aerodynamic profile tuned for efficiency at operational altitudes, and a layout optimized for production scale. The emphasis on modularity simplifies repairs in the field, while standardized components reduce manufacturing delays. This approach produces machines that combine endurance, stability, and adaptability in ways few British aircraft had previously achieved. The engineering discipline developed during this period becomes one of Britain's most valuable assets once the conflict intensifies, and it directly influences the aircraft that will later perform missions demanding extraordinary precision, including the operation that opened this chapter. How did Chadwick transform these early engineering principles into the foundation for a bomber that would reshape Britain's aerial capabilities during the war? As Britain accelerates its rearmament in the late 1930s, the pressure on aircraft designers intensifies. Requirements for long-range bombers grow more complex as the strategic landscape expands beyond local defence. The Air Ministry demands machines capable of sustained operations, significant payloads, and better performance at altitude. Meeting these expectations requires more than incremental improvements. It requires engineers who can reshape structural logic, revise aerodynamic assumptions, and integrate mechanical systems into a coherent whole. Roy Chadwick steps into this environment with a method grounded in analytical discipline and a willingness to challenge familiar design sequences when evidence supports a better alternative. His early studies of load distribution become central to the evolution of Britain's bomber programme. Traditional airframes transfer stress unevenly across spars, ribs, and fuselage members, creating points of failure when weight increases or when turbulence imposes dynamic forces. Chadwick's response is to refine the internal structure so that loads flow more efficiently through the airframe. This approach reduces localized stress, increases durability, and allows the aircraft to support heavier equipment without compromising rigidity. The shift toward more symmetrical load paths also improves stability, particularly during long climbs and sustained turns, where older designs often struggled to maintain consistent behavior. Aerodynamic refinement follows closely behind structural improvements. Chadwick evaluates how airflow interacts with expanding fuselage volumes and larger wingspans. Traditional bombers often face drag penalties when designers enlarge the internal space needed for greater range or payload. Chadwick approaches the problem by shaping the fuselage to guide airflow with minimal disruption, reducing drag while maintaining interior capacity. He studies how the wing root meets the body, how leading edges affect lift generation at different speeds, and how tailplane geometry influences pitch stability during long missions. These adjustments are grounded in practical testing and analytical review, rather than stylistic choices, reflecting a design philosophy driven by measurable results. One of the most demanding challenges involves engine integration. As more powerful power plants emerge, vibration patterns increase in magnitude and complexity. Poorly managed, these vibrations can fatigue structural members, affect control responsiveness, and shorten the operational life of critical components. Chadwick focuses on alignment accuracy, reinforced mounting brackets, and airflow improvements around the engine nacelles. By optimizing cooling and airflow stability, he ensures that engines maintain consistent performance across a wide range of operating conditions. These refinements contribute to more reliable high-altitude flight and improved endurance, both essential to the emerging doctrine of long-distance strategic missions. Chadwick's attention to modular design proves equally important. Maintenance teams require fast, standardized procedures to keep aircraft operational under wartime conditions. Chadwick develops internal layouts that simplify inspections and repairs by separating critical systems into accessible sections. Wiring, hydraulics, and mechanical controls follow paths that minimize interference with structural members, making it easier to trace, repair, or replace components. This modular approach reduces downtime, increases survivability, and supports large-scale manufacturing by enabling assembly lines to operate with fewer bottlenecks. By the time Britain enters the conflict, Chadwick's design principles align with the operational needs of the Royal Air Force, which now requires long-range capability on an unprecedented scale. Missions involving industrial targets deep inside occupied territory demand aircraft capable of flying greater distances with heavier payloads while maintaining structural coherence. Conventional designs face limitations that cannot be resolved through minor adjustments. Chadwick's integrated methodology, built over years of refining structural logic, aerodynamic balance, and mechanical reliability, positions him at the centre of Britain's effort to produce a next-generation bomber that can meet these requirements. As Chadwick consolidates his work, he begins conceptual development on a platform capable of delivering heavier loads across broader ranges than any aircraft Britain has previously fielded. The emerging design incorporates his core principles: a strong internal framework distributing stress predictably, a fuselage shaped for aerodynamic efficiency, a wing structure capable of supporting large spans without inducing excessive torsion, and internal space optimized for both fuel and payload flexibility. The design avoids excess complexity, relying instead on coherence, strength, and adaptability. It is not yet the aircraft that will later mark a turning point in the conflict, but the framework is in place and the technical direction is set. These design choices reflect more than ambition. They represent a response to quantifiable needs. Long-range missions require predictable performance under heavy load. High-altitude operations demand aerodynamic stability and consistent engine behavior. Wartime production requires standardized components and ease of maintenance. Chadwick's design process integrates these demands into an aircraft emerging from disciplined analysis rather than dramatic leaps. The result is a machine that possesses the structural integrity, aerodynamic efficiency, and operational flexibility the RAF requires for missions reaching farther into contested airspace. As the war accelerates and the demand for advanced bombers intensifies, Chadwick's methodology is positioned to deliver an aircraft capable of supporting the most demanding operations of the conflict, including missions defined by precision, endurance, and extraordinary structural resilience. How would Chadwick refine this emerging design into a bomber that could carry unprecedented loads across long distances while maintaining stability under combat conditions? As wartime production expands, Britain faces a challenge that reaches beyond individual factories. The nation must create a heavy bomber capable of carrying significantly larger payloads while sustaining reliable performance across long distances. Earlier designs had provided valuable lessons, but none offered the balance of strength, efficiency, and adaptability needed for the operations that now shape strategic planning. In this environment, Roy Chadwick's analytical approach becomes increasingly central. His work is no longer just about improving components. It is about defining a complete architecture able to withstand the structural and aerodynamic demands of deep-range missions. The design program evolves into a comprehensive response to operational needs. Chadwick examines how to distribute weight across a wider wingspan while maintaining predictable behavior at both high and moderate altitudes. He refines the main spars to handle greater bending moments, adjusts the internal bracing to eliminate unnecessary mass, and shapes the fuselage to guide airflow smoothly along its length. Large bomb bays require a structure that can remain rigid even when empty or partially loaded, and he solves this by reinforcing subtle transition points where the fuselage shifts from curved to flat geometry. These refinements produce an aircraft capable of accepting varied payloads without destabilizing its aerodynamic profile. For viewers following the progression of this project, staying with the analysis helps reveal how each adjustment contributes to the coherence of the final machine. Engine selection introduces new technical hurdles. More powerful power plants promise improved performance, but their integration demands careful alignment and vibration control. Chadwick invests significant effort into evaluating how nacelle placement affects airflow along the wing surface and how changes in thrust patterns influence stability during takeoff, climb, and sustained cruising. Cooling systems must operate efficiently at high altitudes where temperatures drop sharply and airflow becomes thinner. Exhaust arrangements must minimize turbulence that could interfere with flaps or ailerons. Every modification aims to ensure that the aircraft can maintain consistent behavior across long missions, regardless of weather, altitude, or load. Engine reliability becomes a structural concern as much as a mechanical one, and Chadwick's design decisions reflect this interdependence. Internal layout receives equal attention. A bomber designed for long-range operations requires space for fuel, crew movement, equipment, and defensive positions, while maintaining a direct load path that strengthens the fuselage rather than weakening it. Chadwick organizes the internal framework to avoid concentrated stress around access points. He places key systems where maintenance teams can reach them quickly, and ensures that hydraulic and control lines follow clear, protected routes. This thoughtful arrangement reduces downtime, simplifies wartime repairs, and prepares the aircraft for adaptation as operational needs evolve. The emphasis on accessibility and modularity reflects Chadwick's belief that an aircraft's effectiveness is defined not only by performance in the air, but also by its maintainability on the ground. As testing progresses, the new design begins to reveal its full potential. Flight trials demonstrate stability even at heavier loads and show that the wing structure sustains aerodynamic forces without producing excessive twist. The fuselage maintains predictable behavior during steep turns, and the internal framework remains solid after repeated stress cycles. The aircraft manages to carry payloads that exceed previous expectations, while still offering range suitable for the emerging demands of strategic missions. Engineers note how its refined aerodynamic profile reduces drag, allowing it to maintain strong performance across long distances. The design approaches become a benchmark for heavy bomber development, combining structural intelligence with aerodynamic efficiency. These achievements prepare the aircraft for missions that require endurance, precision, and resilience under conditions that test every part of a machine. Long-range operations impose sustained stress on wings and fuselage. High-altitude flight exposes materials to temperature changes that affect flexibility and strength. Defensive maneuvers test torsional rigidity and control responsiveness. Yet the aircraft's behavior remains consistent, validating Chadwick's insistence on integrating every decision into a coherent structural logic. The machine emerges not only as a product of engineering skill, but as a demonstration of how careful analysis and disciplined methodology can create a bomber capable of influencing the broader course of the conflict. For viewers invested in understanding this progression, supporting the channel helps bring forward the deeper engineering stories often overlooked in discussions of wartime aviation. By the time the design reaches full operational capability, it represents a synthesis of Chadwick's principles: a strong internal framework distributing loads predictably, a wing structure optimized for lift across a wide envelope, an aerodynamic shape that minimizes drag without sacrificing internal capacity, and a layout that supports rapid wartime maintenance. Its ability to carry unprecedented payloads while maintaining controlled handling transforms it into one of the most important aircraft produced by Britain during the conflict. This transformation marks a turning point in long-range aviation, demonstrating how engineering insight can fundamentally reshape operational capability. What challenges remained as Chadwick's design transitioned from engineering blueprint to large-scale wartime production? And how would those challenges influence the final stage of development? As full-scale wartime production begins, the transition from prototype to mass output introduces pressures that test every aspect of Roy Chadwick's design. Line workers must translate precise engineering drawings into repeatable assembly processes capable of operating at unprecedented speed. Every jig, fixture, and measurement tool must reflect the structural logic embedded in the original blueprint. Achieving consistency becomes a challenge as the demand for heavy bombers increases rapidly. Materials arrive from multiple suppliers, and slight variations in metal quality or rivet composition can affect the final structure. Chadwick's rigorous tolerances require factories to elevate their manufacturing discipline, ensuring that each aircraft retains the load-bearing capacity, aerodynamic coherence, and mechanical reliability intended in the design stage. Scaling the design reveals engineering details that prototypes rarely expose. Long production runs highlight subtle points where stress accumulates more rapidly than expected, particularly around areas where internal framing supports heavy equipment. Rivet patterns must be adjusted to prevent premature fatigue, and access panels require reinforcement to avoid deformation during repeated maintenance cycles. Even minor modifications prompt comprehensive analysis to confirm that structural integrity remains unchanged. Chadwick insists that every adjustment be validated through calculation and physical testing rather than intuition, reinforcing a culture where engineering evidence dictates decisions. This discipline ensures that mass-produced airframes maintain the same predictable behavior demonstrated by the earliest development models. Operational feedback becomes a crucial influence during the aircraft's wartime deployment. Real missions impose forces that even advanced calculations cannot fully anticipate. Crews report how the aircraft responds under maximum payload, how it behaves during evasive maneuvers, and how it maintains control when damaged by flak or adverse weather. Chadwick studies these reports to refine structural members, redistribute internal loads, and strengthen high-stress zones. The broadened experience of frontline operations reveals how the aircraft absorbs impacts that would compromise earlier designs, demonstrating the value of his integrated approach to structure, aerodynamics, and mechanical systems. Adjustments introduced during production runs further increase resilience, reinforcing the bomber's reputation for reliability across demanding missions. Maintenance requirements evolve alongside operational realities. Ground crews discover which components experience the highest wear during repeated long-range flights. Hydraulic systems, control linkages, and electrical lines require improved routes to prevent chafing or interference with structural members. Chadwick responds by standardizing internal layouts and ensuring that replacement procedures remain consistent across different production batches. The clarity of the aircraft's internal architecture allows technicians to perform repairs quickly, reducing downtime and increasing sortie capacity. This maintainability proves essential as crews push the bomber to its performance limits, flying distances and payloads rarely attempted by earlier designs. As the aircraft proves its capability, its operational role expands beyond the missions envisioned at the design stage. Commanders begin assigning tasks that require both exceptional structural strength and aerodynamic stability under conditions that push the upper thresholds of performance. The bomber carries specialized equipment, experimental payloads, and configurations that demand confidence in its internal framework. Chadwick's decision to prioritize structural predictability allows the aircraft to adapt to these emerging roles without major redesigns. The combination of strength and flexibility makes it a platform capable of supporting operations that require precision, endurance, and controlled handling across hostile airspace. Large-scale production brings additional pressures related to resource allocation and strategic planning. Facilities must coordinate material supply, labor training, and quality assurance to maintain output. Engineers ensure that every assembly line adheres to the same geometric accuracy necessary for the bomber to retain its aerodynamic profile. When shortages appear, substitutions require immediate evaluation to confirm that performance will not be compromised. The collaboration between designers, production managers, and field units becomes essential to sustaining output at a rate that matches operational demands. Chadwick's clear structural philosophy simplifies this coordination by providing a stable foundation that guides manufacturing decisions throughout the program. By the time the bomber reaches full maturity in service, it embodies more than a collection of parts. It represents an engineering evolution built on disciplined methodology, detailed analysis, and careful adaptation to real operational feedback. The machine's ability to carry heavy loads across long distances while maintaining predictable behaviour under combat conditions reshapes the strategic reach available to Britain's air forces. Its structural strength, aerodynamic efficiency, and internal logic form the basis for missions that require exceptional precision. As production continues, the aircraft becomes a symbol of how engineering principles applied methodically can influence the broader course of wartime aviation. How did the aircraft's performance in the field validate Chadwick's design philosophy, and what final conclusions can be drawn about the engineering legacy he left behind?